In the example, we are going to determine the angular velocity and angular acceleration of the shaft. As you may notice, the shaft is spinning about its own axis at constant rate of 3 radians per second. At the same time, it's connected to a system that rotates around fixed axis at constant rate of 4 radians per second. We will start with finding the angular velocity, and this will require building the omega vector. We build the omega vector at specific moment, when the shaft makes a 30 degrees angle with the positive y-axis. As you see, the shaft is spinning around its own axis that makes 30 degrees with y-axis. Notice that this omega vector goes between y and z axis having an amplitude of -3. Treating it as vector, we can split it into its y and z components. Now we can build the omega vector knowing all of its components, x, y and z. Remember that positive value means rotating anti-clockwise, and negative value means rotating clockwise. Before we proceed to the angular acceleration, let's consider this simple system. We will use unit vectors here, ij and k. Now let the system be rotating around z-axis at constant rate. Notice that when it rotates, the system will leave the fixed x and y, although it is still connected to the fixed z-axis. And to solve this issue, we will use an auxiliary coordinates and makes them rotate with our system. Notice how the new coordinates follow the rotation of the system. However, the old z and the new z still coincide with each other. If you look closely, you can see that the instantaneous transition of y' is in the direction of x-axis, and the instantaneous transition of x' is in the direction of the negative y-axis. Now we come to this conclusion. Let's come back to our system so we can proceed with finding the angular acceleration of the shaft. Knowing that alpha vector is the time derivative of omega vector, you need to differentiate all terms and then apply the given values, and you finally get the angular acceleration.